In this section, we continue with the concept of extrema from the last section, now looking at applications of extrema. Let's talk about how to use that concept to find an optimal value, meaning a value that is the maximum or the minimum possible result of some physical example. All right, so let's begin. Here, there's no theorems, there's no definition. It's just an application of what we saw in the last section. So here, let's begin with an example. This might be the first and only section where we begin and end with just examples. Let's find the dimensions. Find the dimensions of a rectangular solid. Now this solid, we want it to have the maximum possible volume. A rectangular solid of maximum volume. Now you might say, well, if it's of maximum volume, I'll just make it infinitely big, right? Which is true. The answer to every question of how big can you make this is always infinitely big. That's why we have to have some kind of restriction. So we want the dimensions of a rectangular solid of maximum volume, which is inscribed in a sphere of radius r. Anytime you have a optimization problem, there has to be something you're trying to make as big as possible, or maybe as small as possible, but there has to be some kind of restriction. Because otherwise, the answer to how big can you make this is always infinitely big. The answer to how small can you make this is always 0. All right? But here, we want to make it as big as possible while still keeping it within a sphere of some radius r. All right, now here I'm going to simplify things ever so slightly by saying, all right, well, this is supposed to be some solid within a sphere of some radius, r. That means that I would have something in all 8 octants. Octants. Yeah. Whenever you have the plane, you have quadrants, 4 of them, 1, 2, 3, 4. Here I have octants, and I have 4 regions above the xy plane and then 4 below the y plane. So here that would give me 8 octants, 4 quadrants, 8 octants. All right, so here I would want a cube, or well, not a cube, a rectangular solid that is within a sphere of radius r. So there's my sphere, and my object, whatever it is, has to be contained entirely within that. All right, well, one thing about a sphere is that it's completely symmetric with respect to absolutely everything you can imagine. So if I can just maximize the size of this in the first octant, well then, multiply by 8, and that gives me the entire object. All right? So here, I'm going to simply stick to the first octant, where everything is positive. And I wouldn't have to worry about positives or negatives or anything like that. So here, I'm going to simplify this slightly by taking advantage of symmetry. If I can maximize, so if we can maximize the volume in octant number 1, where everything is positive, where x, y, and z are all greater than 0, then, by symmetry, the maximum volume of the entire solid is 8 times that much. So that'll simplify some of our computations. All right, so remember, we're trying to optimize the volume of a rectangular solid. Okay, well, what is the volume? Well, it's going to be the length times the width times the height. Okay, that's simple enough. Note here we can say that the length, the width, and the height are simply the 3 dimensions along x, y, and z. So here we can say that's x times y times z. Okay, now, one of the vertices of this solid will have to be at the origin. Okay, since we're dealing with things only in the first octant, then it's got to go all the way down to the origin. On the other hand, you have the other vertex is going to be touching the sphere. Okay, so then that means that since one vertex you want as big as possible while still staying inside the sphere, well, obviously that means you want to go as far out as the sphere. You wouldn't want something that doesn't touch the sphere. That would be too small. You could always make it bigger until it reaches the outer edge. So since one vertex is on the sphere, well, what's the equation of a sphere? Oh, that's x squared plus y squared plus z squared is equal to r squared. It's there's your circle. That's the 3D version of a circle. That's a sphere. Then that implies that z is equal to, now this is one of the nice things about restricting ourselves to the first octant. Here, I know z has to be positive because everything's positive, which means I can solve for z and not have to worry about the plus or minus that I normally have to worry about when I take a square root. So here z is equal to r squared minus, I'm going to move these over, minus x squared minus y squared. And then to get rid of the square that was on the z, I took a square root. And since I'm in the first octant, I don't need to worry about plus or minuses for this one. Normally I would, but here, everything is positive in the first octant. Note, z is greater than 0 in octant 1. Okay, so that means that my volume, I can really think of it as 2 dimensions, right? I don't need x, y, and z. That's x times y times something that involves x and y. R is just a number. Okay, so that means the volume is a function of 2 variables. All right, now we're talking about functions of 2 variables. Here it's going to be f, well, not f, I'm going to say v. V of xy is equal to x times y times z, which we just found. It can be expressed as the square root of r squared minus x squared minus y squared. Oh, but that's what I'm trying to maximize. If I can find the maximum value of v, that'll give me the maximum volume of the rectangular solid in the first octant, and then I can always multiply by 4 and get the maximum volume of, multiply by 8 and get the maximum volume of everything. All right, so there's my function. In my quest to continue to simplify things, I'm going to square both sides. Because after all, if I maximize the volume, well, then that'll also maximize the square of the volume. All right, the bigger this is, the bigger this is. All right, if that's 10, well, then that'll be 100. If I can make that even bigger, well, that'll make that even bigger. You say, okay, that's true, but why do you care about squaring it? Because I don't want that square root there. So we can write that as x squared times y squared times r minus x squared minus y squared. Okay. Here I can distribute that, and that'll give me x squared y squared r squared minus x to the 4th y squared minus x squared y to the 4th. So what I'm going to try to do is I want to maximize this one. Okay, well, if I maximize this one, that'll automatically maximize that one. Okay, so now what? Well, I can maximize things, as I saw in the last section, by finding the first and second partials and then figuring out where the critical numbers are, and then testing to see which, if any of them, are maximums. Note, I said if any of them. It is possible that some of these questions don't have a solution. Now this one does. I've done this one ahead of time because this one's complicated enough. I wanted to do this ahead of time to make sure, to confirm it. Before the recording of this lecture, I went ahead and did the problem myself. But it is possible to have some problems where in the end the answer is there is no maximum value. It's not possible to maximize it. But here, but those are not very common, and especially for our applications, and that's not what will happen here. So here, let's see. We're going to find the first partial with respect to x of v squared. All right, well, the derivative with respect to x is simply take your 2, bring it down, subtract 1 from the power. Everything else stays the same. So that'll be 2xy squared r squared minus 4x cubed y squared minus 2xy to the fourth. Note here you have a common factor of 2xy squared. So we can factor that out, 2xy squared times, if I factor out 2xy squared, I'm left with r squared minus 2x squared minus y squared, like that. I also want to find my first partial with respect to y. Okay, so that's going to be the derivative with respect to y of this v squared function, and that's going to be 2x squared y r squared. With respect to y, that'll be minus 2x to the fourth y. And again, with respect to y, that'll be minus 4x squared y cubed. Note that these also have a common factor. They have a 2x squared y to the first. 2x squared y to the first. And if I factor out 2x squared y, I'm left with r squared minus x squared minus 2y squared, like that. So these are my first two partials of v squared. So now I can find critical numbers by finding where these are undefined or where they're both equal to 0. Okay, so now looking for critical numbers. Or I keep saying critical numbers. Looking for critical points. Looking for critical points. We note that neither v sub x squared nor v squared sub y are ever 0. Oh, sorry, they are 0. They are never undefined. Are ever undefined because they're polynomials. Polynomials are defined for all real numbers. So here we don't get any critical points from that statement. However, we can check to see if they are ever simultaneously 0. Okay, so let's see. V squared sub x at x comma y equals to 0, and v squared sub y at x comma y equals to 0. We want to solve that equation. Okay, so that'll be this equals to 0 and this equals to 0 simultaneously. So that will be r squared. Well, let's see. Let me write that in. Well, that's fine. That'll be r squared minus 2x squared minus y squared times 2xy squared. You might wonder why I wrote those backwards. No reason. I just started writing that one and I forgot about this one. So, I mean, it's a product. It doesn't matter which way we write it. And then here we take r squared minus x squared minus 2y squared times 2x squared y, like that. Okay, equals to 0 and equals to 0. Now, one obvious solution is 0, Because if both x and y are equal to 0, then that means that that's 0 times something, and 0 times something, and that's all going to equal to 0. Okay, so obviously one solution is 0, 0. Okay, but, well, what if 0, 0 is not the solution? Okay, well then that means that the solution is not coming from these, right? If x and y are not 0, well then that means that this won't be 0. So that means that my solutions are coming from this part. So here that means that if my solution is 0, 0, great. If my solution is not 0, 0, it must come from this other stuff, so I don't even have to worry about that part. It'll be r squared minus 2x squared minus y squared, and r squared minus 2, that should be minus x squared minus 2y squared. All right, well, I can solve this with just addition. Let me go ahead and multiply the bottom row by -2. So that'll leave the top row the same as r squared minus 2x squared minus y squared equals to 0. But now let me take the bottom row and multiply it all the way across both sides of the equation by -2. So that's -2r squared plus 2x squared plus 4y squared equals to 0. And now if I add those two equations, I get -r squared. That's going to be 0, and that's going to be 0. But right here, I'm going to get 4y squared minus y squared. That's 3y squared. So now I can solve for y. Let me go ahead and add that over to this side. So that'll give me 3y squared equals to r squared. That means y squared is equal to r squared over 3, which means that I can take the square root of both sides. Notice I don't need to worry about plus or minus because, again, in octant number 1, everything is positive. So here, normally this would be plus or minus, but note, in octant 1, y must be positive. Okay, there we go. We found our value of y. Okay, but if we find our value of y, then we also have to find our value of x. Okay, so let's go and take that and plug it back into one of our equations, starting from, well, I guess we can just plug it into any one of these. So here that's going to give us, so if y equals the square root of r squared over 3, then that means that r squared minus x squared minus 2 times that is equal to 0. So now I can solve for x. Let's see here. I can go ahead and move these over this way. Oh, you know what? Let me go ahead and... Oh, let's see. How do we want to do this? Yeah, that's not going to be very nice to solve. Here, these are not going to be like terms, since that's the square root of r squared. That's just r. And that's r squared. These are not going to be a nice thing to combine. So instead of doing that, we could do that, but that's going to be an algebraic nightmare. Instead, let's just go back and use the same system that we had before, and we can solve for x as well. Notice that the two equations look very similar with respect to x and y. So here it should be just as simple to solve for x as it was for y. You might say, that was simple? Relatively speaking. All right, so here, I started by multiplying the bottom row by -2 to try to get rid of my x. Instead, let me try to multiply my top row by -2 to get rid of my y. So from here, instead of going this way, let me go this way. If I multiply the top row by -2, that'll give me -2r squared plus 4x squared plus 2y squared equals to 0. And then the bottom row I'll leave alone. That's going to be r squared minus x squared minus 2y squared equals to 0. And since those are now lined up as like terms, I can eliminate them. Let me add the two lines together. and this will give me negative 2r squared plus r squared will simply give me negative r squared. Adding these together, 4x squared plus negative x squared will give me a plus 3x squared. Adding these together gives me 0, and adding those together gives me 0. So here that'll give me that 3x squared is equal to positive r squared. If I add that over this way, divide by 3, and then I can take the square root of both sides. And there's my result. Here I get, again, only the positive root because, again, in octant 1, note, in octant 1, x must be greater than 0. Okay? If we were not in octant 1, well then plus or minus would both be valid. Okay, so here we can, well, in fact, we can even simplify those, right? The square root of r squared over 3, that's going to give us, well, let's see, I can take the square root of r squared over the square root of 3. I can split the numerator and the denominator. This will give me r over root 3. I can then rationalize. Multiply top and bottom by root 3. And we're left with r root 3 times r over 3. So that looks like that's going to be our value for both x and y. And that's the positive root. So we're going to have root 3 over 3r, comma, root 3 over 3r. So those are our two critical points. So now from these, we're going to need to test these. Now, here it seems pretty obvious that 0, 0 is not the maximum. In fact, it seems pretty obvious that's the minimum. The smallest object that I can have, rectangular or otherwise, is going to be one with dimension 0, right? 0 length, 0 width, 0 height. So it seems pretty apparent that that's going to be our answer. But we can never assume, right? Because sometimes you'll have some that don't have a solution. Or sometimes you'll have some that have two solutions that are different. Here, again, it's fairly obvious that's not going to work. But still, let's go through and check everything. Also, because this is an example, and, well, frankly, I'm doing all the work. So for this one, I think you should want to go all the way through to the end. All right. So let's go ahead and take a look at that. To summarize, we have critical values. I keep saying values. Critical points, 0, 0, and root 3 over 3r, comma, root 3 over 3r. So now we need to check those. We had v squared. We took the partial with respect to x. And that was 2xy squared r squared minus 2xy to the fourth minus 4x cubed y squared. And I'm just copying down from the last page. That way I don't have to keep flipping back and forth. If I take v squared and then take the partial with respect to y, that result was 2x squared y times r squared minus 4x squared y to the third minus 2x to the fourth y. Okay, so those were our first partials. Now let's take a look at our second partials. V sub xx, or v squared of x, v squared sub xx. All right, well, the first partial with respect to x was this one. So now the partial of that with respect to x will give us 2y squared r squared. That'll give us 2y to the fourth, well, minus. And then with respect to x, that'll give us minus 12x squared y squared. If we now take v squared sub y, that's going to be the partial of this one with respect to y. So that'll be 2x squared r squared. With respect to y, that'll be minus 12x squared y squared. And with respect to y, that would be minus 2x to the power of 4. And then our mixed partial, remember, as long as everything's continuous, v squared sub xy will be the same as v squared sub yx. So here we only need to find one of them. Here we're going to find v sub xy. So here's v sub x. Now take the partial of that with respect to y. That'll give us 4x, 4xy r squared minus, that'll be 8xy cubed minus, that'll be 8x cubed y. So now we're going to go ahead and find the value of d, which is v squared sub xx at, here we're going to go ahead and use this one. That'll be root 3r over 3, comma, root 3r over 3 times v squared sub y, again at that point, minus, we're going to take the mixed partial at that point, and that whole thing is squared. All right, so let's see what we get. If we take this and plug it into v sub xx, here, that's going to give us, let's see. If you square cube root of r, square root of 3r over 3, if you square that, you just get r over 3. There's a 2 there, so that's going to be 2 times r over 3, and then that's r squared. Oh, sorry, that should be r squared over 3. Let me try that again. If I go ahead and plug that into here, that's going to give me a 2. Squaring that point will give me r squared over 3. When you square root 3 over 3, you get 3 over 9, which is 1/3. And then times your r squared. Minus, here we're going to take 2 times, again, take your y. Now you're raising it to the 4th power. Well, that's really just the square of this one. So this would be r to the power of 4 over 9 minus, and that's going to be 12. If you square this number, again, you get r squared over 3. And then if you do it again, that's another r squared over 3. So that's going to be r to the 4th over 9, like that. And now that's being multiplied by this expression here. Okay, so that's going to be v squared sub y. And we're going to plug that in here. Okay, so that'll give us 2 times, we're going to take this number and square it, which gives us r squared over 3 times r squared minus, that's going to be what, 12 times, again, we're going to take that number and square it, which is r squared over 3, and then again that same number and square it, which will give us another r squared over 3. That'll be r to the 4th over 9 minus 2 times, that's going to be this number raised to the 4th power, which again gives us r to the 4th over 9. Minus, okay, so now we're going to take this and plug it into v squared sub xy. Okay, so that'll be this number times that number. Okay, well that's going to be r squared over 3. So that's going to be 4 times x times y. That'll give us r squared over 3 times that r squared minus 8 times that number cubed times that number. That'll give us that'll give us r to the 4th over 9. That's the same as that one over there. And then over here, that's minus 8. And then here, since these are the same number, it doesn't matter if you have x cubed y or y x cubed. It doesn't matter which one the cube is on. Since these are the same number, I'm going to get still 8 r to the 4th over 9. And then that whole thing is being squared. Okay, that simplifies quite a lot though. Let's see, that's going to be, these are all r to the 4th power. So really just worry about the numbers. That's going to be 2/3 minus 2/9 minus 12/9 r to the fourth times that's 2/3 minus 12/9 minus 2/9 r to the fourth, okay, minus, and then here that's going to give us 4/3 minus 8/9 minus another 8/9 r to the fourth, and that whole thing is squared. So here if we subtract these, that'll give us what? 6/3 minus, 6/9 minus 2/9, that'll give me 4/9. 4/9 minus 12/9 is negative 8/9. So negative 8 over 9, negative 8 over 9 r to the fourth times, that's the exact same number, negative 8 over 9 r to the fourth. And then that, well, let's see, that's 12/9 minus 8/9 is 4/9 minus another 8/9 is negative 4/9 r to the fourth squared. This will give us negative times a negative, that's a positive, 64 over 81 r to the eighth, r to the fourth times r to the fourth. Here that's going to square, make that negative go away. So that's going to give me positive 16 over 81. So there's a minus out here, minus 16 over 81 r to the eighth, which in the end, after all that, gives us, 64 minus 16, that gives 48 over 81 r to the eighth, which is certainly positive. After all, r is the radius of a circle. It's got to be a positive number. So a positive number times a positive number is definitely positive. So here we do find that d is greater than 0. So that means we do have an extrema. And so we go back and we look at f sub xx at that point. Which we saw was, I guess I should say v squared sub xx, since that's the name of our function here. So if we go back, that was this expression here, which simplified down to this expression here. So that was negative 8/9 r to the fourth, which again, r is a positive number. So that's going to be a positive times a negative. That's going to be a negative. So you have an extrema because d is greater than 1. But then, that should be, right, that's greater than 0. It doesn't, I said it's positive, and then I said it's greater than 1. This is greater than 0 since it's positive. So that means that it's an extrema. And then by noting that v squared sub xx is less than 0, then that means that you end up with, in fact, a maximum. So you have an extrema, that is a maximum. Okay, so if we go back and plug in 0, 0, you will note that everything's just 0. And if you find v squared x, that'll be 0 minus 0 minus 0. Everything is 0. Right? There are no constants. Everything is x or y or both multiplied together. So here everything would be 0, and so that clearly would not be a extrema. So then that means that we have only one extrema, and this is our result that we were looking for. So to maximize the volume of the cube, well, it is a cube, I think, because these are the same, but let me go ahead and call it what they called it, the rectangular solid. Once again, note that that's only going to give you the distance across this way on the positive half. So if this is giving us, okay, that's how far we're going, root 3 over 3r, that's really telling us how far we're going from here this way. Oh, but we want the dimensions all the way across. Okay, so we're going to double everything. So it looks like we have a value of, again, either 0, 0, which we know we don't want. It looks like this point right up here was going to be root 3 over 3r, comma, root 3 over 3r, comma, and we'll find a third point here. Well, let's see. We can always just plug into this value here. We know z is equal to the square root of r squared minus x squared minus y squared. Well, we now know what x and y are, so we can plug those in. So that gives us that z is equal to the square root of r squared minus, again, if you square that x, you're going to get r squared over 3. And if you square that x, you're also going to get r squared over 3. So that's r squared over 3 minus r squared over 3. So 3r squared over 3 minus 1r squared over 3 minus another r squared over 3. That gives us r squared over 3 inside the radical. But as we see over here, that was the same result. So that'll give us just r over the square root of 3, which we can then rationalize to give us root 3r over 3. So it turns out that this was a cube. So that's the point, root 3 over 3r, comma, root 3 over 3r, comma, root 3 over 3r. But again, the question was find the dimensions. Okay, well, root 3 over 3r gives me the distance from here to here, or from here to here, really, every direction. So what I want to go is I want to go all the way across. Oh, okay, well then just double each of these, right? This is just giving me the dimensions up here. Oh, but then I can go ahead and double across. So the maximum volume of the rectangular solid is found with a cube, because they all have the same side lengths, of dimensions. So we're doubling that one, so that would be 2 root 3 over 3r by 2 root 3 over 3r by 2 root 3 over 3r. That volume, again, we can either take the smaller number, the root 3 over 3r, multiply those together, and then multiply by 8, because we're going to find this in all 8 octants, or more simply, we can just go directly to this result and multiply it together. Here, notice that 2 times 2 times 2, that's the 8 anyway, so either way, you're going to get the same result. So if we multiply all of these together, we end up with the maximum volume of the rectangular solid is found with a cube of dimension this by this by this, with the volume, well, let's see, that's 2 times 2 is 4 times 2 is 8. Root 3 times root 3, that's just 3, and then another root 3, over 3 times 3 is 9, times 3 is 27, and then r times r is r cubed, which is, here the 3 goes into 27 9 times, and so your maximum volume is going to be 8 root 3 over 9 r cubed. Units cubed. So this is our result. You find this maximum volume with these dimensions. At this point, I usually say, well, you might want to try this, but, well, you might not want to try this, but I'll give you a chance to do it anyway. This is not a course in applications. This is not a course in engineering or physics. This is a course in calculus and math. So here, this is one of the few times where we see a realistic-ish looking application. But since this is not the main focus of our course, here we're going to see 2 examples, and that'll be the end of this section. Right? Here we don't want to show 100 cases of 100 different possibilities of finding extrema. We simply want to give two slightly more realistic examples in order to help us practice finding extrema of functions of two variables. So go ahead and give this one a try. This one is a little simpler than the one we just did computationally. It does use the same ideas. It is the same kind of problem. It's just computationally a little simpler. A rectangular box is resting on the ground. Okay, well, that's not very mathematical. Is resting on the xy plane. So the visual being, you have a box that's sitting on this plane right here, the xy plane. Now I'm not going to draw it just yet because there's some more conditions here. All right, one of the vertices is at the origin. One vertex of the box is at 0, 0, 0. Okay, so one vertex is back here. Okay, so without any particular dimensions, here we're going to go ahead and just draw some kind of rectangular solid right here. All right, so one of the corners is right there at 0, 0, 0. Okay, now we want to maximize the volume of the box, but we have a condition. This rectangular box, which is laying on the xy plane, and where one of the vertices is at the origin, has the opposite vertex in other words, this one over here. Let's go and do that in red. All right, one is at the origin. The other one, right up here, is on the plane 6x plus 4y plus 3z equals to 24. So there's some plane out here like that. So this is coming up to this. So this plane is kind of limiting the amount of space. You have all the space. Imagine you have, the corners of two walls is the corner of a room. You're trying to put something in the corner of the room, and then you're covering it with this sheet. But the sheet is going to be anchored there, there, and there. Okay, so you want stuff to be behind the sheet. You don't want it poking out. So the question is the obvious one. Find the maximum volume of the box. Here you have a function of 3 variables, but note it's not difficult to write z as a function of 2 variables. It's not hard to write z as a function of x and y. You could also write y as a function of x and z, or x as a function of x and y, but since you're on the xy plane, you may wish to be using those variables anyway. So go ahead and pause the video, give this a try. And once you're done, go ahead and unpause the video and we can go through it together. All right, so here you're already in octant number 1, so everything's already positive. All right, here you're on the xy plane and everything's up above here. Here, this 6x plus 4y plus 3z equals 24. Okay, so then that means that my corner is out here in the first octant. Okay, so we're going to maximize the volume of the box. Now remember, the volume of a box is given by length times width times height, which we can just call x times y times z. Now, since one of the vertices is on this equation, since one vertex is on 6x plus 4y plus 3z equals 24, then we can have a further restriction on z, saying that z is equal to, well, let's go and subtract these over and divide by 3. So that'll be 24 minus 6x minus 4y divided by 3, like that. Or it may be a little nicer to just write this as 1/3 times 24 minus 6x minus 4y. All right. So that means that the volume is really a function of two variables, x and y, where you have x times y times z. There we go. Here I can go ahead and distribute my xy, so that I can write that as 1/3 times 24xy minus 6x squared y minus 4xy squared, like this. So now I can find my critical values. Let's find v sub x at x comma y. That's going to be the derivative of all of this. That's going to be 1/3. With respect to x, that's going to give me 24y minus, take your 2, bring it down, so that'll give me 12xy minus, with respect to x, that's just the 4y squared. If I find v sub y at x comma y, that's going to be 1/3 times, with respect to y, this derivative would be 24x minus 6x squared, and then here that would be minus 8xy. Note here that I have a common factor of y, and over here I have a common factor of x. So I can write this as y over 3 times 24 minus 12x minus 4y. And I can write this one as x over 3 times 24 minus 6x minus 8y. All right, now I'm looking for critical points. Notice that this is never undefined. These are all polynomials. Looking for critical points, we know v sub x and v sub y are never undefined. They exist, they're defined for all real numbers, so we don't get any critical numbers from there. However, we do have solutions to y over 3 times 24 minus 12x minus 4y, and x over 3 times 24 minus 6x minus 8y, both equal to 0. Here, one obvious solution is x and y are both equal to 0, because that would be 0 times something is 0, and 0 times something is 0. So one obvious critical point is 0, 0. You'll find that happens kind of a lot because, well, obviously one critical point, if it's available, if it's possible given the conditions, is going to be 0, 0, because that's the minimum. The smallest something you can get is 0 if you're measuring a size. Okay, so, well, what if it's not 0, 0? Well, then I got 0, 0 from these. So if it's not 0, 0, then I'm looking at just these. So I'm really looking to solve the equation, the system of equations, 24 minus 12x minus 4y equals to 0, and 24 minus 6x minus 8y is equal to 0. Here, if I know that my critical point is not 0, 0, then it's not coming from these. It's got to be coming from this or this equal to 0. Or not or, this and this equal to 0. I can now solve my equations for either x or y. Here, let me go ahead and just multiply the top row by -2. What that'll do is that'll make that a -48. that'll make that a positive 24x, and that'll make that a positive 8y equals to 0. Flip all the signs, double everything. Then this will be 24 minus 6x minus 8y equals to 0. And then if I add those two lines, I get negative 48 plus 24 is negative 24. 24x minus 6x, that's plus 18x. And then adding these gives me 0, and adding those gives me 0. And so now I can go ahead and solve for x. Add your 24 over to the other side. That'll give you 18x equals 24. And so x is equal to 24 over 18, which really is 4/3. All right, so there we go. I have x is equal to 4/3. So I guess I'll write that as 4/3, comma. And then I can solve for y by just plugging that in there. And since this doesn't have anywhere near the unpleasantness that the previous problem did, this one I actually could just plug in. That should be fairly nice to work with. Let's go ahead and do that. I'll take the bottom equation and plug in x is equal to 4/3. And hopefully that one works out nicely. So since x is equal to 4/3, then that means that 24 minus 6 times 4/3 minus 8y equals to 0. Just taking that equation, plugging in what I now know that x is equal to. If I take 4/3 times 6, that'll give me 8. So 24 minus 8, that's 16, minus 8y is equal to 0. You can go ahead and subtract the 16 over that way. So that'll give us negative 8y equals negative 16, which implies that y must equal to 2. So that is my other critical point. These seem to be my only solutions to this system of equation equal to 0. I have two critical points, 0, 0, and 4/3, comma 2. It seems apparent that it's got to be this one. But again, let's check it. I know v sub x at x comma y. That's equal to 1/3 times 24y minus 12xy minus 4y squared. So that means that v sub xx will be the derivative of this one with respect to x. Notice that both of these are constants with respect to x. So the derivative is 0. So really we're just left with this one. 1/3 times the derivative of negative 12xy with respect to x is just the negative 12y. And here that simplifies to give us a negative 4y. A third of negative 12 would be negative 4. We could find v sub xy by taking this and taking the derivative with respect to y instead of x. So that would be 1/3 times, with respect to y, you get 24. With respect to y, you get minus 12x. And with respect to y, you get minus 8y. We know v sub y at x comma y is equal to 1/3 times, I've already forgotten what it was, 24x minus 6x squared minus 8xy. And again, I'm just looking at the previous page, just copying that down so we don't have to flip back and forth so many times. Here is v sub x and v sub y. So now I want to find v sub y. All right, the derivative of this with respect to y is 0, 0, and negative 8x. So I guess we can just write that as negative 8/3 x. So now d is equal to v sub xx at, well, we had two critical points. We had 0, 0, and we had 4/3 comma 2. Seems pretty obvious that 0 is not going to work, because if we plug in zeros, that's going to be 0 times 0 minus the square of 0. Oh, actually, it won't. It will be 0 times 0 minus 8, which is going to be a negative. We only get extrema when we have a positive value there. Okay, so let's go ahead and use the other one here. So v sub xx is, what was our point? Oh, 4/3, comma 2. And then we're going to take v sub y at the same point, multiply those together, and then minus v sub xy at the same point, and then that value is being squared. All right, so we're just taking 4/3, comma 2 and plugging it in right here. Notice there's nowhere to plug in your x, so just plug in your y. That's -4 times 2, that's -8. If you're taking v sub y, we're going to plug in 4/3. There's nowhere to plug in your 2, so just the 4/3. -8/3 times 4/3, that's -32/9. And then if you're taking v sub xy, that's this one, you're going to plug in 4/3 and 2. Okay, well that's going to be minus, all right, let's see here, that's going to be, that's 1/3 of 24, which is 8. You're going to plug in 4/3 right here, 4/3 of 12, that's 16, but then you're dividing that by 3, so minus 16/3. And then you're plugging in y is equal to 2 right there. -8 times 2 is -16/3. And that whole thing is being squared. All right, so let's see. That's going to give us, well, that's a positive. Let's see, 8 times 32, that's carrier 1, 256/9, minus, that's going to be 24/3, minus 16/3, that's going to be 8/3, minus another 16/3, that's -8/3. The whole thing is squared, so that's 256/9, minus, squaring a negative makes it a positive, 64/9, and that'll give us 192/9, and those can be divided by 3, so that'll give us 64/3. So there's our value of D, which is clearly positive. So since D is positive, that does give us an extrema. Okay. So then we go back to v sub xx at that point, 4/3, comma 2, which we found was -8. Okay, so we have an extrema because this is greater than 0, but because v sub xx is less than 0, then that means that that extrema must be a maximum. If it's greater than 0, that's a minimum. So there's our result. That's what we're looking for. We're looking for an extrema. Incidentally, if we do look the other way, if we want to find v sub xx at 0, 0 times v sub y at 0, 0 minus v sub xy at 0, 0 quantity squared. If you plug in 0 to this, that's 0. If you plug in 0 here, that's also 0. That's going to be 0 times 0 minus. If you plug in 0 to this one, that's going to be 24 minus 0. That's 24. Divide that by 3. 24 divided by 3, that's 8. And the thing gets squared. So this gives us 0 minus 64, which is -64. Here, that is not greater than 0. That's less than 0. So here this would actually be a saddle point, which is not what we're looking for. We're looking for an extrema, and in particular, we're looking for a maximum. So in this case, that must mean that our result is this one here. So going back to our question, we were supposed to find the volume of the box. Okay, well, the maximum volume is where this corner is at, let's see. We have, so the maximum volume is where the vertex that is opposite the origin is, okay, so what point do we have? We have 4/3, comma 2. Now this is a point in space from our illustration. it looks like we need a z. Oh, but from the very beginning, we said z is equal to 1/3 of this thing. Okay, so let's see here. So z is equal to 1/3 of 24 minus 6 times our x value minus 4 times our y value. So that's going to be 4/3, comma 2, comma, let's see, 4/3 of 6. It's going to give us 8. 2 times 4 is also 8. 24 minus 8 minus another 8. That's going to be 8. Oh, but then divide that by 3. It's going to be 8/3. So it looks like the dimensions of our rectangular solid of greatest volume, we'll see this point over here at 4/3, comma 2, comma 8/3. Oh, but since one dimension is at the origin, that means that the x-coordinate gives me how far out I went along the x direction from the origin. The y-coordinate tells me how far along the y direction I went from the origin, and the z-coordinate tells me how far up I went from the xy plane. So here, these are not only the coordinates of this point, but they're also my dimensions of my cube. That's because one side was at the origin, so here these must tell me the displacement in every direction. So the maximum volume is where the vertex opposite of the origin is 4/3, comma 2, comma 8/3. So the dimensions of the solid are 4/3 by 2 by 8/3 for a maximum possible volume of 64/9. Cubic units. Cubic inches, cubic feet, cubic miles, or whatever. And that's our answer. The dimensions of our solid are there for a maximum volume of 64/9 cubic units. And that's the end of our problem. Once again, this is not of central concern to this course. These are simply meant as examples to the previous topic of finding extrema. Should anybody have any questions, comments, or problems, make a note of those and reach out. And I hope everyone has a nice day.